Welcome, everybody. It's a privilege and a delight to be able to give this talk tonight. I'm really glad to see that ANZUS doing such a great job of advancing science, promoting science, and basically taking science to the people. I think we're in an age where scientific modes of thinking have been perhaps prey to other more dangerous modes of thinking, and it's kind of important for democracy that people think about what science is and how it works and what its values are and what its place ought to be. So I'm here to tell you a bit about what I do in my day job, which is a field of mathematics called topology. I think it's kind of fun. Yeah, given that it's sort of talk about advancing science, I thought I might just begin by sort of just saying something a little bit broader about promoting science and why it's important. Yes, because I think, the acceptance by the general population of science and what it means is an important thing. And I came across this quote recently. I read it a long time ago. It's from a book by Carl Sagan, the great astronomer, and Andrew Yoon, record producer and science communicator. And it's from a book from 1995 called The Demon Haunted World. Recommended. You know it already. A bestseller in its day. This is 1995, and they write of a foreboding. They're talking about America, but it certainly applies to Australia and much of the world. A foreboding of America in their children or grandchildren, like that's today, when awesome technological powers are in the hands of very few, yes, and no one representing the public interest can even grasp the issues, when the people have lost the ability to set their own agendas or knowledgeably question those in authority, and clutching our crystals and consulting our horoscopes, our critical faculties in decline, unable to distinguish between what feels good and what's true. We slide almost without noticing back into superstition and darkness. And yeah, it's okay. So there's perhaps, you could argue there's a bit of a hyperbole there, but, I think it's a really prescient description. I think it's quite a few people have noticed in recent times, of all the science fiction dystopias, the Blade Runners and the Terminator 2s, this is possibly the one that sort of got it most right. So they continue on, the dumbing down of America, Australia, most evident in the slow decay of our substantive content and influential media, 30-second or 10-second sound grabs, lowest common denominator programming, credulous presentations on pseudoscience and superstition, and especially a kind of celebration of ignorance. So yeah, I just think that is an important thing to kind of mention in the present day, especially about advancing science. There is one science fiction dystopia that I came across recently that is very popular and you may have seen. This movie here, if you haven't seen it, again, I recommend. Don't look up, although it's more of a sort of allegorical documentary in the present day about a comet coming to strike Earth, but it's sort of an allegory for willful blindness to science and climate change. Okay, anyway, so yeah, I sort of read that back in the 2000s, I think, when I was a PhD student. And at the time, I sort of thought, no, these guys are on the wrong track. I thought that was the time of sort of mass internet adoption, the sort of idea of Web 2.0, and that science and democracy were sort of on a trajectory to produce a lot of progress and human flourishing. I was involved in some projects myself around that time, but yeah, things perhaps in many ways didn't turn out the way I hoped, and it seems that this is a better prediction. Anyway, so that's not the subject I'm going to talk about in detail today, but pessimistic predictions aside, I think it's also good to have a vision for what a scientific sort of democratic society looks like. And there's one from one of my favorite mathematicians. This fellow here, this very stern-looking fellow, is Bertrand Russell, a great mathematician, philosopher, social thinker, thinker on pretty much every topic under the sun. And he has a really, if you haven't read it, I mean, everything by Bertrand Russell is pretty much still worth reading in the present day. He has a wonderful essay from 1926 called Education and the Good Life, in which he describes what a scientific society, scientific temper looks like. So yeah, I think it's worth reading. So neither acquiescence in skepticism nor acquiescence in dogma is what education should produce. What it should produce is a belief that knowledge is attainable in a measure. You can get some of it, though with difficulty. That much of what passes for knowledge at any given time is likely to be more or less mistaken, but that the mistakes can be rectified by care and industry. In acting upon our beliefs, we should be very cautious, where a small error would lead to disaster. Nevertheless, it's on our beliefs that we must act. This state of mind is rather difficult. It requires a high degree of intellectual culture without emotional atrophy. But though difficult, it is not impossible. In fact, it is the scientific temper. Knowledge, like other good things, is difficult but not impossible. The dogmatist forgets the difficulty. The skeptic denies the possibility. Both are mistaken, and their errors, when widespread, produce social disaster. So in some sense, it's a simple, it's not a short, not a soundbite message, but I think it's a simple and moderate and reasonable message. It's what in practice a lot of scientists do in the way they do things. It's not an easy answer, but I think it's one that applies just as well today as in written. And if you think about that and compare to what we see from our culture today, from media, public figures, and perhaps even communicators, it's not the sort of it's sort of almost a message from another world, but it's a good world. I think it's a good vision that we should try to get to. Anyway, so those were just some general considerations, and coming from a mathematician, I thought they were relevant today. All right, so let me go on and try to explain something about maths research. And I'm going to start with some excuses for my own job here. And I think that as far as explaining scientific research to the public, mathematicians probably have it hardest. Yes, I am totally excusing myself for my difficulties I'm going to have over the next hour or so. So why? Let me give you a few reasons. So the first thing is that the average person has no idea what mathematics research looks like. I think the average person probably thinks that a research mathematician like myself is just really good at sums, do really big sums. And if you look at about as good as you're going to get for most people, you see things like this. Beautiful Mind, which is actually a documentary about a real person, although sort of person with big mental health issues, John Nash. And the other ones there are screen grab from Good Will Hunting, where we learn that if we stand in front of a blackboard and cancel fractions, then we can have high fives, and that's maths research. So there are blackboards often involved in maths research. Sadly, there's not that many blackboards in production today. We do tend to like blackboards. But yeah, these are not really accurate of what maths research looks like. And I guess another sort of big issue is that a lot of people have experiences in school of mathematics, which totally shapes their view of mathematics. And in many cases, it's not a great experience for people. But it's also a very sort of finite system of things that you learn in the curriculum. Whatever the case of the sort of the content that you learn, it is quite, I'd say, something of an indictment of the school system that you can come through 13 years of school, learn maths in every one of those 13 years, and yet at the end, not know what research is. I certainly didn't when I finished school. And in saying that, I don't want to, I don't think those who are teaching mathematics are the problem. I think maths teachers do a very difficult job under difficult circumstances, and and working under a lot of constraints on the whole, do a really good job. But nonetheless, there's a problem there. I can tell you what maths research is. I'll just tell you. It's basically problem solving where you get a new solution. So when I solve, when I'm doing maths research, it's just problem solving, except I can set the problem. And if I make up the question and I can answer it, and that's a new result. You don't have to make up the question because there might be other people might have asked the questions. I guess your solution has to involve something new. Otherwise, there's nothing new to report in your research. But it can also involve sort of, especially in applied mathematics, involve experiments or case studies or model simulations, many other things. And it may involve lots of collaborations. Increasingly, it does. It may involve high fives. It may involve blackboards, but it probably also involves conferences, a lot of talking, perhaps a lot of social activity as well, a lot of frustration, a lot of difficulty, but eventually progress, hopefully, in many cases. There's also mathematicians. I guess mathematicians are, in many ways, not the greatest at explaining their work to the public. But that's a problem for me, not for you. One mathematician taking their maths to the public that I would like to mention is my Monash colleague, Burkhard Polster, who has a really wonderful YouTube channel called The Mathologer. So if you haven't used YouTube and you want to check it out, if you haven't already, I recommend. We've also got the difficulty that maths is hard, and it's ancient. It's probably the oldest of the sciences, and it's very specialized in the present day. So, I guess people have been thinking about mathematical questions for thousands of years, and it's now so advanced and sophisticated that, like in most cases at least, in order to make progress, you have to spend an enormous amount of time working on what geniuses over centuries and millennia before you have done before. You work on very difficult technical problems, and then maybe you can push the frontier of knowledge a little bit. So it's in the nature of the subject to be quite difficult. And often you now have a situation where you're a specialist in one subfield and you can't understand the next subfield over. So these will contribute to the difficulties of the subject, but they also mean that you're standing in a long tradition, a sort of culture that goes back centuries and millennia, and you stand upon this sort of massive edifice of human knowledge. Another difficulty, and perhaps the last one I'll mention, is that it is often removed from applications, especially pure maths. So by its nature, pure maths, the questions are pure. They're in themselves. They're sort of motivated by mathematics itself. You build upon previous mathematics, you generalize, you abstract from previous theories, and you continue this process over centuries. So you end up with these extremely abstract theories that just become further and further from everyday experience. And it's growing ever faster. So the average person might think that maths is sort of finished when you finish high school, but in fact, here's a graph of the number of maths papers published every year. And if you can't see the y-axis there, it goes up to like 300,000. So it's like in the order of hundreds of thousands of new research papers being published every year. It's an enormous subject and very difficult to keep up with even in your narrow specialization. I should also say, because a lot of the things I'm going to mention don't have direct applications, that when you're doing maths, you cannot tell at the time whether that will have any applications or not. For one thing, it's fundamental knowledge. So, it often has, it answers a lot of general questions across a wide sort of variety of fields and answers to a lot of problems. And some of them might turn out to be practical. Sometimes it leads to further theory that then gets applied. And sometimes there's very direct applications, just like 3 centuries in the future. So anyway, it's very fundamental and it's also very fun. And so that's what I'd like to tell you about tonight. All right, so let's get stuck into it. What is topology? And even here, it's a difficult subject to define what it is. So if you go on Wikipedia, you see something like this. So the properties of a geometric object that are preserved under continuous deformation, such as twisting, crumping, and bending. That is without closing holes or opening holes or gluing. So that's a very vague definition, and if it feels vague, I agree. If it feels like it's not precise, I also agree. It can be made precise, and I'll try to do some of that tonight. Another definition that you sometimes see, here's another encyclopedia definition, what's often called rubber sheet geometry. So the idea is that 2 objects are considered the same. You imagine them made of like stretchy rubber, and if you can turn one into the other by stretching and squeezing, but not ripping, not tearing, not poking a hole in the object, then you consider those 2 objects the same. Okay, so the classic example is that a topologist considers a coffee cup and a donut as the same. There's the animation there. If you had a donut made of sort of stretchy rubber, you could turn it into a coffee cup, as that animation shows. And similarly, equally classically, but perhaps not quite as well known, is the idea that a cow is the same as a sphere. So it's sometimes a phrase you hear from mathematicians, a humaspherical cow. So that's often the pejorative, like we make too many simplifying assumptions. But nonetheless, from the point of topology, it's quite accurate. So there's a cow getting made of rubber, I suppose, being morphed into a cow. I guess you have to ignore the existence of the digestive tract or other ears and nose and throat. Also that there are gaps between cells. Also that there are gaps between molecules. Okay, don't think too hard about it. But roughly speaking, spheres are the same as cows. Okay, so that's a sort of vague definition. And if you study topology, that's not what you're going to learn. So I thought I would just show you the actual definition, also to show you why I won't show you any more proper definitions. One other thing I should say is that, before I do that, is that these 2 things are not equal. So although the sphere and the cow are the same, and although the torus and the donut are the same, the cow is not the same as the coffee cup. And maybe that's not, maybe that's intuitively reasonable. It's actually not, may not be easy to sort of prove mathematically. Somehow you could get from a sphere to a donut by sort of poking a hole in it, and that's precisely the kind of violent thing you're not allowed to do in topology to make an equivalent object. So these turn out to be non-equivalent objects. All right. Yeah, so as I say, this is the sort of rough definition that you often see in encyclopedias and in popular presentations, but there is a real definition underneath it, which, yeah, I'm not going to show you this for the purpose of understanding it, just to show you that there is one and that there's a reason I wouldn't do it. All right, so yeah, here's another. So here's a very standard definition of what a topology is. There's a set together with some subsets involving the empty set, union of sets and intersection of sets, and it's quite abstract. Yeah, so if you study an undergraduate course in topology, you'll see something like this. And it does present a precise notion, and when you understand that in context, it does actually explain why you are considering things up to continuous deformation, something you can actually understand it that way, but it takes a lot of background. And as I say, this is something that comes, it builds upon centuries of previous notions. So I think this, as far as I know, this definition dates from about 1922, and it builds upon previous things over the previous century, and it got more and more abstract until today you have this beautiful, elegant, incomprehensible definition, which is quite characteristic of pure mathematics. It's beautiful if you understand the previous subjects. So unfortunately, I can't do that tonight, but I just want to show you that these things exist and they're out there, and with hard work, they can be understood. Speaking of a measure of work possibly producing knowledge, here's Uncle Bertrand Russell again, and this sort of illustrates, you get this kind of abstract things which are, which he describes here. So in another essay, Russell writes that mathematics rightly viewed possesses not only truth but supreme beauty, a beauty cold and austere. And you can sort of see, when mathematics is presented in this way, it's certainly cold and austere, but when understood in context and in history, it has this beauty to it, like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, that's yet sublimely pure and capable of a stern perfection, such as only the greatest art can show. So I just don't want to put that out there because I don't want to give you the impression that this is just a vague, woolly subject of like morphing things around, which is largely what I'm going to do for the rest of this talk. All right, so let's press on. And so we talked about how there's the donut / coffee cup, there's the cow / sphere, and these are examples of surfaces. So so one question in topology is like, what other ones are there? So here we're going to consider them as surfaces. And in mathematics, in geometry, and in topology, a surface normally just means a two-dimensional thing. So there we have a two-dimensional space. I've sort of drawn more standard versions of a sphere and a donut, or technical name is a torus here. And so if you have an intuition of what a two-dimensional surface looks like in sitting in three-dimensional space, could be curved in many ways, but it's just sitting there, that's probably a pretty good intuition of what a surface is. And so one sort of first question in topology is, well, what are the possible surfaces? We've seen two here, two classes of surfaces. Are there any others? Let's sort of think about what it means to be a surface and sort of what sort of questions we can ask to make this a precise question. So one thing about a surface is that locally, they all look the same. So if you pick any point on that sphere or any point on that torus, or any point on the cow or the coffee cup, locally, in a certain sense, they all look the same. If you sort of lived on that surface as a sort of two-dimensional being, a local neighborhood of where you live would look like a two-dimensional disk. Might be curved up a bit, but this is topology, so we don't care if things are curved up a bit. Somehow it's always a disk. And so surfaces are all locally the same. What makes them different is sort of globally how they connect up and how they close up on themselves. Okay, so yeah, a very sort of first topological question is, what types of surfaces are there? It's a classic question in topology. It was answered in the 19th century, and there are different answers depending on precisely how you define what a surface is. And it's a good illustration of how mathematical theorems work and how mathematical research goes. If you just ask what type of surfaces are there, it's a bit of a vague question. Let's try to make it more precise. I've made it a bit precise with this sort of definition. Locally looks like a disk. But let's say a little bit more. We're going to require, as I said, that our surfaces are sitting in three-dimensional space in a sort of smooth way, and they don't pass through themselves. The technical name for that is embedded. It's embedded in three-dimensional space. I don't want it to go off to infinity. I want it to sort of sit in a finite region of space. That's a notion called compact, whatever that means. And I'm going to avoid saying there's a boundary. So I don't want to consider things like disks, which have a boundary. So let's sort of consider those surfaces. So the question is, what are the possible types of surfaces embedded in three-dimensional space in a finite region without boundary? So here are two examples, the sphere and the torus. Are there any others? But we sort of want to consider certain things the same, like the torus and the same as the coffee cup and so on. And yeah, so there's technicalities here. So when are two surfaces the same? So there's a definition called homeomorphic. And homeomorphism is a continuous bijection with continuous inverse. If you know it, that is great. If not, don't worry. It's roughly what we were saying before about being able to morph it around in three-dimensional space. That's not exactly the same. Anyway, so let's see if we can think of any more and try to generate a complete list. Okay, so we've got the coffee cup donut torus. We've got the cow sphere. Are there any others? Well, you could think of the disk we were talking about before, but that disk sort of had boundary. So no. Yeah, or maybe I should ask the audience. Did anybody think of any others? Double hole donut, perfect. Well, I think I put something else on the slide next. Mobius strip, that's kind of a fun one. So that's what you get when you take a strip of paper and give it a half twist. And yeah, it's kind of a fun one, but it has boundary, so it doesn't count, unless I think the fun. There's a picture of one. And the fun thing about Mobius strips is that they're what we call non-orientable. So if you sort of imagine going around on that band there, you start off on, say, at the front here. I'll use my cursor rather than point. Where's my cursor? Here it is. Yeah, if you start off at the front here, you sort of go around, you'll be on the back here. You go around, then you come under here, and you'll be on sort of the back here. You come back to where you started, and you're on the opposite side. So like the front and the back side are actually the same side. That's kind of fun. So yeah, here's a nice picture of it by MC Escher, showing ants crawling around. You can follow the ants around from one side to the other. And you also see it in lots of places like recycling symbols and Mobius strip, Google Drive, Mobius strip. Anyway, but they all don't count for our purposes because they have a boundary. Yes, but all right, so we're going to see a double hole torus. Yeah, so we've seen the sort of sphere in the torus, and they have a property called genus. The sphere is known as genus 0, and the torus is genus 1. It's basically the number of holes in it. Yeah, so indeed, well done, audience. So this idea of a double torus like this, which is also known as a genus 2 surface, that works. Sort of what we call genus 2. And then once you've got holes, you just keep adding more holes. So there's a genus 3 surface. Now there's a different genus 3 surface, sort of adding the holes in different places. But yeah, you can sort of see, like you could imagine morphing one into the other. So they're equivalent. Here's an interesting way to think about it. You can think of it sort of as a ball with handles attached. That's sort of a very nice way to classify them. And also Nutrigrains. Nutrigrain is a genus 3 surface, usually. Yeah, also pretzels tend to be genus 3, although they can vary. Yeah, and so this not very nice theorem to consider surfaces of any genus. Genus G means that you have a sphere and you add G handles to it like this. So this very nice theorem from the 19th century, although perhaps not rigorously proved in the 20th. It's called the classification theorem for compact surfaces. And yeah, so it says that any one of the types of surfaces we're considering, compact surface without boundary, embedded in three-dimensional space, is topologically equivalent to one of these. So this is a complete list, and it's a sort of it's an answer to a mathematical question. So it sort of illustrates the process of doing mathematical research. You ask a question, a natural question perhaps, depending on your predilections, how natural it is. You narrow it down with assumptions to make it a precise, sort of answerable, reasonable question. You might have a guess as to what the answer is, and then you prove it. So I'm not going to have time to prove it. Sort of in an undergraduate course on topology, you might give a proof of this. So it's a very nice theorem and a classic one. And it's sort of a model for other dimensions as well. All right, so yeah, that's a sort of very pure theorem. It also comes up in other contexts as well. So here's topology in another context, entertainment. So I'm old enough that I know this game. I don't know if other people here know what Pac-Man is. It's an arcade game. It was very popular in the 1980s. Yeah, I guess I grew up playing a bunch of Pac-Man. It's quite gender specific. I was looking around for a bit of gender equity, and there is, turns out, a Ms. Pac-Man game. Yeah, so I would have thought Pac-Woman or something else would be better, but turns out it was Ms. Pac-Man. And it's actually, yeah, so there was actually a nice story about this recently, about where it comes from. So a few years back, there was a story about the MIT dropouts who, instead of doing their theses, wrote as Pac-Man, firstly as a sort of hack, and then they sort of became legal. And they first had a name of Crazy Otto, then they had Pac-Woman, but they thought it didn't roll off the tongue. So they changed it to Mrs. Pac-Man, but then one of their wives didn't like that, too patriarchal, so it became Ms. Pac-Man. So it's an interesting mix of like yeah, social norms and feminism. But anyway, so there's a male and a female version of Pac-Man. And yeah, so it's got topology to it. So one interesting thing about this game for our purposes is that you can go off the screen and come back in on the other side. So that's called wraparound in the sort of world of game development. So it's when an object moves off one side of the screen and comes in on the other. So yeah, when you're playing Pac-Man here, you've sort of got one spot you can go off the screen on the right, come in on the left. In Ms. Pac-Man, there's sort of more possibilities. Okay, so in order to think about this from the point of view of surfaces and topology, we'll consider an idealized version of this game. So what's happening in this picture is we're imagining that like you can go off the screen anywhere on the top and you come back in on the bottom. So here is Pac-Man going off the top of the screen, coming in on the bottom. Here's Pac-Man going off the right-hand side and coming in on the left. So we're imagining we can sort of go off any point of the screen and we sort of come back in on the opposite side. And a nice way to describe this is by taking a square like this and putting arrows on it like this. So this is sort of saying that this red arrow is the same as this red arrow. When you go off at one point on that red arrow, you come in on the other point, that red arrow. And same for the blue arrows. So it's like those two red arrows are the same arrow. It's like they're glued together. And so when you do that, what you're going to find is that these video games are played on a surface which is not the plane. So can anybody see what surface it is? It's sort of gluing up the red and then the blue, perhaps. So it's illustrated. So you get a torus in the end. So if you take that square and you glue the top and bottom together, you get a cylinder, but then you've got the left and right to glue as well. So you end up with a torus or a coffee cup, depending on what you're looking, how you see it. So what you've got here is, yeah, this game is actually played on torus. So there it is, sitting in sort of in these video games. You've got the topology sitting there, and this idea of wraparound. And there's a nice website you can go to, run by a topologist, geometrygames.org, a guy named Jeff Weeks, and you can actually play games like this. So I don't know if I quite have time to do it. Maybe I'll show you some other things instead, or I can show you afterwards. But you can actually sort of play versions of video games which are sort of played on the torus or indeed other more complicated versions of wraparound. Okay, so that's sort of surfaces in 2 dimensions and wraparound. Well, there's no reason you can't do it in other dimensions too. And this is a way to understand what spaces can look like in other dimensions. So let's consider some 3-dimensional wraparound. So just as Pac-Man can be considered as a square with sort of the edges sort of glued up, you can do the same in 3D. You could consider like a 3D version of Pac-Man or Ms. Pac-Man, where you take a cube rather than a square, 3-dimensional version, and you do wraparound on that. So like when you go off the right-hand face, you come in on the left-hand face. When you go at the top, you come in the bottom. And it comes front to back. So what you're doing then is you are gluing faces together. And that's a bit harder to do in 3-dimensional space, but yeah, it's interesting to visualize. So yeah, what does it look like? Well, if you think about it, if we go back to 2 dimensions here, if you are Pac-Man and you're sort of living on this space, if you look ahead, what you see, the world doesn't end at the edge of the square. It connects back to the left-hand side. So if you look ahead, what you see is your own behind. If you look up, you see your own bottom. So you sort of, what you see is sort of copies of yourself. What you see in reality is sort of a tessellation of squares. And you're sitting there being one of these, in one of these squares, but there are all these other squares which are sort of copies of yourself. In fact, they are also you. It's because space wraps around and you see those other copies of yourself. So what you see in 3 dimensions is a similar thing. Now, if you look out one side, if you're in that cube and you look through the cube, through one of the faces, you see another copy of yourself. So what you're going to see is something that looks kind of like this. And yeah, so what we've got here is a tessellation of cubes filling 3-dimensional space. And you sort of, but all those cubes are really the same cube wrapped around. And yeah, so what you get there is a 3-dimensional space that's got an interesting topology to it, coming from this kind of 3-dimensional wraparound effect. Yeah, so that's sort of a 3-dimensional version of Pac-Man. And you can do it with other things too. So why stop at cubes? You can take other polyhedra too. So here's a fun example. You can take a dodecahedron and you can sort of say, well, if I go off the top of the top pentagon of that dodecahedron, I'll come back in on the bottom and I'll specify how. Sort of a certain twist, not exactly aligned. And you do the same for all of the 6 pairs of pentagonal faces of the dodecahedron. And yeah, that space, it turns out, was it's got a name. It's called the Poincare dodecahedral space, named after this guy, Henri Poincare, a big mathematician from the late 19th, early 20th century. I don't think he described it this way. This comes later. So it's another example of mathematics getting simplified as you go through time, or abstracted. And what does that look like? Well, you can actually draw pictures of this stuff. You can simulate it. And what you get is a tessellation of dodecahedra in 3-dimensional space. And you again see copies of yourself. And in fact, there is a flight simulator available for these kind of spaces. And yeah, I've got it on my computer. So I thought maybe I'll show you. So let me go to that other screen. And I think for people on Zoom, I'll need to share this other window. So just give me a second here. I should share this one. Yeah, so this is the 3-dimensional torus, or the 3D Pac-Man. So that's the sort of cube. And let me see if I can fly around here. Yeah, so I try not to give anyone too much vertigo by turning too abruptly. But yeah, so that's what it would look like to live in a 3-dimensional toroidal universe, 3-dimensional wraparound space. Those other Earths are like, they're not in some sense copies of the Earth. They're all the same. It's just that space wraps around and you see copies of yourself. Yeah, so you go around. So you're seeing a tessellation of cubes here. All right. This so this is all available from this website, geometrygames.org. Freely, you can download it and play with it yourself. Let's do the dodecahedral space. So yeah, we can fly around in this one too. So here we've got tessellated dodecahedra. And yeah, so we're seeing a similar but more weird and complicated thing. And so topologists that study 3-dimensional spaces, so study these kinds of things and what's going on in these kind of spaces. So I guess in some of my research, I consider some of these spaces and the things you can say about them and study their sort of topology. That's me. I'm a spaceship. So yeah, that's you. Yeah, that's us. As we fly around, we're seeing ourselves. I'm about to crash into the Earth. Oh well. Yeah. So yeah, so you're free to play with this, and there are a lot of other spaces that you can use. Yeah, and you can imagine, like, there are many polyhedra out there, many ways you can glue the faces. If you do that, you don't. Sometimes things can go wrong at the corners, but basically you can build a lot of 3-dimensional spaces that way, or 3 manifolds, as we call them. Okay, yeah. So as that kind of flight simulator suggests, it raises sort of questions about astrophysics or cosmology. Like, does this happen in our actual universe? Do we have this sort of wraparound? Do we have a shape to our universe like that? And so astronomers, cosmologists have studied this question. And so what you're seeing here, so this is a picture of the cosmic microwave background radiation. And what you can do with it is like look for, so if the universe did have this kind of wraparound effect, you should see copies of yourself, or at least copies of yourself, millions or billions of years back, depending on how long it takes the light to get around, wrap around the universe. And what you can see there are 12 circles in this picture, and that's like the best fit, or like finding 12 regions that are the same. And if you look at those 12 circles, they don't look very much the same. So that was sort of an attempt to fit to the universe to sort of punctuate dodecahedral space. You can try for other spaces too, but basically on the current evidence, it's probably not the case that the universe has wraparound. Probably topologically, the spatial universe we live in is topologically trivial. So this goes on. But nonetheless, regardless of whatever the universe turns out to be, there's a mathematical question of what the answer could have been. What are the possible shapes of a three-dimensional space universe? Now, in the two-dimensional case of surfaces, I sort of told you basically the answer when we talked about the classification of surfaces. Classifying three-dimensional spaces is much, much harder, but it's seen a lot of progress. So it's an area of active research. So there's been a lot of progress in the last 30 years, and basically I do research in this area too. But yeah, that gets much harder. So let's go, rather than go up to sort of where number of dimensions is too hard, let's go down. So let's talk about one-dimensional topology. So one-dimensional things are basically curves. But the thing about curves is that they can get knotted up. So this leads to another interesting area of topology, and one that I kind of work in. So we all know what knots are. They go back a long way. This is basically an accurate idea of what knotting is mathematically as well as practically, with some important qualifications, which I'll get to in a minute. So we all know knots from when we tie our shoelaces and do things like this. And knotting is sort of just like a lot of mathematics. It's one of the areas of mathematics that goes back furthest in history. I'm going to claim that it's the area of mathematics that goes back the furthest in human history, because there's evidence that goes back to prior species than humans. So yeah, I thought it'd be fun to mention just that knots go back to prehistory. And it's one of the sort of core technologies, one of the earliest technologies in human civilizations. And there's even evidence that Homo erectus had it. So this is a paper on the topic. Yeah, so there are these Homo erectus sites, 300,000 years old, which have perforated objects. And it's these sort of bones and stones and things with perforations in them. And it's very hard to think of a reason why people would perforate things other than to put a cord through them, like a bead or something. So it appears that Homo erectus had knots. And in fact, we know that, some apes can knot too. They can do knots. So it's not a lot of evidence that it's seen in the wild, but some apes that have been sort of raised in zoos and sort of with humans certainly can knot. So here's a picture of an ape named Watana doing weaving. It goes back a long way. All right. Also in mythology. So knots appear in ancient mythology as well. So this is the current state of a town known as Gordium. It's in present-day Asian Turkey. It used to be the kingdom of Phrygia. And yeah, there's this great story from ancient mythology where the king of Phrygia, Midas, also known for a golden touch, tied an ox cart to a post, and a prophecy was made by an oracle that, so it's a very complicated knot, and a prophecy was made that whoever could resolve that knot would go on to rule all the world, or rule all of Asia. And then Alexander the Great came along, so the story goes, and at least according to the sort of dominant version of the myth, Alexander tried to untie the knot by conventional methods, but then sort of the oracle had not said you had to like untie it, so he just got his sword out and just sayings about the Gordian knot and cutting the knot. And as a topologist who regularly gets frustrated by difficulties with knots, I sympathise. Yeah, so no, knots go back a long way. So they've got this wonderful history to them. Anyway, yeah, so go through the modern day. Here's the wonderful, the modern standard reference on actually tying knots, as opposed to the mathematical theory of knots. This book called the Ashley Book of Knots. I highly recommend. I was looking for my copy in the office today, but it seems someone borrowed it. It's in high demand. It was made by Clifford Ashley, who was a sailor and artist. And there's a wonderful group today called the International Knot of Guild Tiers, which has an interesting relationship to mathematicians, as I may mention as we get there. All right, so anyway, knots go back a long way. Well, let's get back to the sort of mathematical track. And for the purposes of mathematical knot theory, for us, a knot is a closed loop in three-dimensional space. strictly speaking, it should be smooth, so it can't pass through itself. Got a sort of precise statement in the brackets there, but something like this. So that is what we call the trefoil knot, because it looks a bit like a clover, 3 leaves type sort of thing. Here's another knot. It's called the unknot because it doesn't look very knotted. And so the basic question in knot theory is, given knots like this, are they the same or different? So if you had that knot in the left, sort of sitting there as a rope, could you sort of just, without ripping it or passing it through itself or cutting it Alexander style, could you morph it or move it into the unknot? So if you think about it, probably not. The fact that they've got different names suggests not. Yeah, yes, not knotted. So yeah, it's you have lots of linguistic fun in this subject. But then there are tricky ones. So here is a diagram of a knot as well. Is that the unknot? Hard to tell. And even so proving that this and this are different is maybe something you convince yourself of beyond reasonable doubt with a piece of string, but mathematically proving it is something that's really perhaps kind of hard to imagine how you would do it. Proving that 2 knots are the same, though, is not that hard. So if you had a piece of string here, it is actually the unknot, and you just have to sort of show how to do it. So this is meant to be an animation that shows how do I do it. So proving that 2 knots are the same is sort of the easy thing. You just have to find the process of unknotting and how to do it. But showing that 2 knots are different is often a really hard thing to do. And classifying all the different knots is like the basic problem of knot theory. It's a difficult problem. There's a lot of active research into it, including what I did. So let's talk a bit about what you can do with knots. So I guess I'm skipping forward from ancient mythology now to about the 19th century. So this gentleman here on the left is Carl Friedrich Gauss, great mathematician. And he introduced an idea about the linking of curves. So whereas a knot is one curve, a link is more than one or more disjoint knotted loops. So something like this. So that's a specific link. It's a link of 2 components because there are 2 curves there. It's called the Whitehead link. So the two curves are sort of drawn in blue and red. And you might notice it's got arrows on it. You sort of need arrows on the knot. You've basically put a direction along each curve. This is called an oriented link. You sort of need it for this thing to work. And what Gauss introduced was a concept called the linking number. It's sort of a numerical measure of how linked one curve is with another. So this was in 1833. And the way it can be done, which again is actually not how Gauss did it. Gauss wrote down some massive integral, because Gauss could do that kind of thing. But later on, other mathematicians found a simpler way to describe it, which is to look at the crossings. So in this diagram, there are sort of several crossings, and there are some pluses and minuses there. And the thing is that when you've put the arrows on the curves like that, every crossing basically looks like one of the 4 there. Either the red or the blue is over and under, and then there's sort of a sign to, depending on which way it could go. Basically, if you get your right hand out and you point your thumb in the direction of one of the curves, then if the other finger sort of point in the direction of the other curve, it's sort of a plus. And if the right hand doesn't work, the left hand works, then it's a minus. So it's sort of a handedness to each crossing. And what you can do, the linking number is defined to be the number of pluses minus the number of minuses. Okay, we divide by 2, but that's not so important here. So it's coming from this sort of sign to each crossing. Yeah, so it's a really nice idea. And this math talk now even has numbers in it, which is a first time number. Anyway, so for this example here, the linking number between these 2 curves in this link, there's 2 pluses and 2 minuses. So the linking number is 0. And yeah, so we could even do a few more examples. So the linking number is now just something you can work out. If you've got a link with 2 curves, you can put some arrows on it and you can work out these pluses and minuses. So if you put that link there with, it's just 2 circles so linked with each other in possibly the simplest way. And if you look at the way I've put the arrows on, turns out the 2 crossings are negative. So you get 0 minus 2. So you end up with a negative linking number. Here's an even simpler one. It's called the unlink. Linked. Just 2 completely disjoint circles. And working out the linking number for that is even easier because there are no crossings at all. There are no positive ones and no negative ones. And the nice fact about the linking number is a theorem which basically goes back to Gauss, that these diagrams give you linking numbers, but if you move the diagram about, if you move the knot about and get a different diagram, you always get the same answer for the linking number. So even if I were to take that hop link and move it about in space and like make it all tangled up so that it doesn't look the same, but it's the same link, I'll still get the same answer for the linking number. It will still be -1. And the unlink as well. Even if I were to move those circles around some complicated way through each other, I'll still end up with an answer of 0. So if you move a link around, you get the same number. And this is actually an example of what we call a topological invariant, because it doesn't vary. As you sort of make topological moves on the thing, this quantity remains invariant. And so this actually gives you a way to prove that the two links here are different. So corollary here, because we've got two different answers for the linking number, you can't unlink the hop link there on the link on the left. If you could, then there would be a process of moving one to the other, and in that process, the linking number would stay the same. So they would have to have the same linking number. But they don't, so they can't be unlinked. And so, yeah, you might have thought it was pretty obvious that that was linked and that wasn't, but this is a way to prove it mathematically. And so a lot of what people do in knot theory and in topology and in mathematics more generally is look for things in invariant quantities under the sort of moves that can happen. And the linking number is a very simple one. It doesn't tell many links apart. If we go back to the link on the previous page, I think we've got an answer for 0. But that's using other invariants, you can show that it's not the unlink. So it's what we call a weak invariant, but a simple one. And so, yeah, often what you find is that there are some invariants which are easy to compute, but not very good at distinguishing things. Other things are very hard to compute, so hard that you can't do it. Okay. So the thing I was going to mention next was moving forward to the 1860s, when science took a spectacularly wrong turn. So this person here, you may have heard of, there is a temperature scale named after him, Lord Kelvin. He had this wonderful idea. This was around the time that Dalton was producing the atomic theory of elements and so on. And Kelvin had this wonderful idea that the different elements were different types of knots in the ether. He published a paper about it. It was a wonderful paper. So very great theory, very falsifiable, was absolutely falsified. So good theory, not the right theory. His student, Peter Tate, however, sort of took this, and it really spurred a lot of mathematical research into mathematical theory of knots. And so what Tate did was he started tabulating the possible knots and made the first sort of tabulations of knots. So here is a diagram, a table from his papers in 1884, the first 7 orders of knottiness. Wonderful way to put it. And then he made a whole lot of conjectures, but they sort of remained completely unproved for 100 years. These things called the Tate conjectures, which were proved much later. And these were the precursor of tables of knots which exist today. So today, if you look online, if you Google knot atlas, you will find enormous tables of links and knots. And here's the start of it. So there's the trefoil, there's the unknot, many, many more. So they go on, they grow very quickly. It's sort of hard. And it's easy to, it's really hard to tell them apart. And classifying them is like not an easy thing to do. All right. So skipping forward 100 years, getting closer to the present day, I'd like to introduce you to this man, Vaughan Jones, who sadly passed away just a few years back, a New Zealand mathematician. He discovered a new invariant of knots. So we saw the linking number before. He discovered something that's now known as the Jones polynomial while studying something called von Neumann algebras. And you don't need to know what von Neumann algebras are, just that they've got nothing to do with knot theory. So it's a really good example of just the complete indeterminacy of mathematics. Doing pure mathematical research in one area may well have massive applications into a completely unrelated field. You just never know. So this is what happened to Vaughan Jones. As a result, he won the Fields Medal in 1990. And even more prestigiously, he was made vice president for life of the International Guild of Knot Tiers, 1992. So he was, I once saw him give a talk where he was basically regarded this as his greatest achievement. So it's simple enough that I can basically tell you how to do it, how to calculate it. So for each knot, it gives you a polynomial. And in school, we learn about polynomials. We normally use the variable x. In knot theory, for some reason, we tend to use the letter A. So anyway, I'm going to use the letter A here. So that's just a picture of the hop link from before, 2 linked circles. And what we're going to do, so I'll first define something called the bracket polynomial, and then from that, the Jones polynomial. So here's how it works. For each knot, there's a way to do algebra on it and get a polynomial. And this is the definition. This is how it works. There are three simple rules. So the first rule is, if you've just got the unknot, it's 1. Okay, so if you've got unknot, answer's 1. That's all the first rule is. Second rule is the sort of key one. If you ever see a crossing in a knot, so this diagram sort of represents a crossing somewhere in the middle of a knot, what you can do is resolve it. And there are two ways to resolve the crossing, to change those strings so that they join up without crossing in the picture. And what you do is you pick up a factor of a for one of them and a factor of a to the minus 1 for the other. And what that allows you to do is progressively simplify them. Okay, and then the third rule is, if you ever see an unknot sort of sitting in your picture, you can get rid of it. So you've got unknot and then a sort of knot or link diagram. You can get rid of the unknot bit and just leave the rest of the picture, provided you put in a factor of that, minus a squared minus a to the minus 2. Why a squared minus a to the minus 2? Good question. Yeah, there are actually quite deep reasons for that. Okay, but we can calculate it. So that's the bracket polynomial. Yeah, and this is how you do it. So here's a sort of fact that you can, bit of a calculation that you can do. So sort of fact here is, if you ever see a sort of just a little whirl, a kink in your knot, you can get rid of it at the cost of introducing a factor of minus a cubed. And the kink goes the other way, it's minus a to the minus 3. And the way it works is that you just sort of do that sort of step of resolving the crossing. So there's a crossing here, and I can resolve it in two different ways. And one way I get a sort of extra circle, the other way I don't get an extra circle. So for this one, I pick up a factor of minus a squared minus a to the minus 2, whatever it is. And this one is just as if there were no whirl in the first place. So when I work that out, yeah, I just end up with the fact that removing the whirl gives you that factor. Great. And that's not the Jones polynomial. And in fact, you can sort of see that, like, in this picture here, these two knots, when you put a whirl in it, like, it's the same knot. So it's not good that you get different answers. You get this sort of extra factor. But basically, if you just correct for that factor, that's what the Jones polynomial is. So the Jones polynomial of a knot is a polynomial in this in pronumeral a, where you take this bracket polynomial made up this way, and then you just put in some extra factors of minus a to the minus 3 to sort of cancel out this stuff. So you have minus a to the minus 3 to the power of w of k. And w of k is just a number. And it turns out it's basically the linking number we described before, positive minus negative. So you can actually calculate it. So yeah, here's a calculation I did earlier. Here's the hop link that we had from before. And you can resolve one of the crossings. There are two crossings. I resolve one of them two different ways. Get my factors of a and a to the minus 1. And now this is, they're both unknots now. So that's an unknot with a whirl in it in one direction. That's an unknot with a whirl in the other direction. So you can use the previous fact. You can work out what it is. And yeah, if you check the algebra, you end up with minus a to the 4, minus a to the minus 4. That's the bracket. And then if you want to work out the Jones polynomial, you just correct with a factor of minus a at the front. It turns out to be a factor of minus a to the 6. And so you end up with that. And this is a polynomial invariant of knots. So you can calculate this thing, and you can work out when knots are the same or different. So you can distinguish a lot of knots this way with fairly simple calculations. So this was the big breakthrough that Warren Jones made, which made him vice president for life. All right, I'm almost out of time, but maybe I'll just say one more thing. Bringing together three-dimensional spaces from one-dimensional space, from knots. So here we're coming into the sort of the 21st century and a lot of recent research. So if you've got a knot in three-dimensional space, you've got the one-dimensional space, but then there's a three-dimensional space around it. And that three-dimensional space is a very interesting three-dimensional space. It has sort of wraparound in it when you wrap around the knot. And one thing that topologists consider is to consider the space that's called the complement of the knot. So the space around the knot, so it's a 3D space, it has wraparound, and often it has a very nice geometry. So these two gentlemen here made huge breakthroughs in thinking about this. This is William Thurston, Fields Medal for his work on three-dimensional spaces. And I think basically he made a lot of breakthroughs and also a conjecture, sort of an educated guess, that basically all three-dimensional spaces, and especially the three-dimensional spaces around knots, can be given a really nice geometry so that you can sort of basically fly around them in a flight simulator. I'll show you in a minute. In an appropriate sense. So I guess I don't have time to define it properly. And then this person is Gregory Perelman. Around the turn of the millennium, he basically gave a proof of it, which was, very incomprehensible. But now, some years later, basically, the mathematical community believes it's true. So this is sort of this sort of gave it, in some sense, a classification of three-dimensional spaces. Let me just try to give you a flavor of how it works. So here is a knot. This is a knot called the figure 8 knot. And that's a 3D space with wraparound. Thurston, or actually I think it was known a bit before Thurston, but Thurston sort of popularized it, showed that if you take two solid tetrahedra and you glue up the faces like they're indicated there, that's actually, so that's like a three-dimensional space with wraparound. He showed it's the same as the knot complement, the complement of that, the space around that figure 8 knot. That is not at all obvious. And that is when you do a PhD in low-dimensional topology, you have to spend a month of your PhD staring at these pictures until you understand why it's true. But nonetheless, it is true. And so as a result, what you can do is you can think of these three-dimensional spaces as very nice geometric three-dimensional objects. And in fact, what I can do is show you what it looks like inside this. So this is a piece of software called Snappy, which is research software that we use, but it's freely available. Let me just share for people on Zoom. And what you can do on this, let me just load up the figure 8 knot. Let's just check I've got the right one. Okay, it's showing on a different screen. Okay, there it is. Bring it across. Okay, that's the right knot. Good, so I've got the right one. Let's have a look at it. Oh, it's opening up in another window again. Yeah. So if we look at this, I guess I probably need to share this window. So what this is the polyhedron, which you can glue together to get the three-dimensional space. So I think that's a polyhedron with 12 triangular sides, and they're colored. There are 2 of each color, and you glue them up. So that's sort of describing sort of wraparound space as a sort of space with as a polyhedron with faces glued. And then you can fly around it too. So let's see if I can figure out how to do this. Inside view. Yes, but it's in a new window. Okay. So here it is. Here it is. And yeah, so I can share that window. This one. And what we're seeing here is what it looks like inside this knot complement. So these edges are the edges of the tetrahedra I was just showing you. These balls are like where the knot is. And yeah. So yeah, there's a three-dimensional space. And if we fly into one of these, what we see is this is actually tessellated squares, which tessellate a torus. The boundary of when you look at the curve around if you consider your knot as a thickened up curve, its boundary is like a torus, it's like a donut. And what you're seeing here is that boundary tessellating these squares, tessellating this sort of two-dimensional surface. Anyway, so lots of fun. And in my research, when I don't know what to do, I can just fly around knots like this. So these are the sort of things that we study, and these are the sort of things that we do. All right, so I'm just about done. So maybe I just thought I'd leave you with a nice quote from a mathematician, Mariam Mirzakhani. She was a wonderful mathematician, passed away just a few years ago, first woman to win the Fields Medal. And she has a wonderful quote just about studying mathematics in general. I thought I'd just read it. I don't think that everyone should become a mathematician, but I do believe that many students don't give mathematics a real chance. I did poorly in math for a couple of years in middle school, just not interested in thinking about it. I can see that without being excited, mathematics can look pointless and cold, but the beauty of mathematics only shows itself to more patient followers. So I guess I'll stop there, and if you have questions about anything, I'll be happy to take them.
So I'll take Chairman's privilege to ask you the first question, which is when you're talking about surfaces and edges and so on, it made me think about fractals. So is there any relationship or overlap or intersection between fractals and topology and this sort of stuff?
Yeah, absolutely, absolutely. I guess in these things I was doing, I sort of said they were smooth at times. That was precisely so that fractals didn't come up. So that's the assumption that, yeah, it sort of makes the fractals go away and it makes something simpler. But if you don't put that assumption in, you can get fractals everywhere. Yeah, so there are really interesting knots that are fractal. They're called wild knots, because they can go wild. So that's sort of a subfield of knot theory called wild knot theory. And what you can sort of get is, yeah, and sort of surfaces too. So there's a famous surface called the Alexander Horn sphere. So basically, you take a sphere and you put a handle on it, except you don't quite let it join up. You make a horn. And then on that horn, you make another horn. So they almost link. And those horns again and again. And you get this sort of beautiful fractal structure. And it's so linked up that you can't unlink it in a continuous way. Yeah, so it sort of has, yeah, so in many ways, it's as if it were linked up, but somehow isn't in other ways. Yeah, so there's a lot of interesting questions to ask, absolutely.
Play around with something. Some experience that this goes on.
Yeah. Yeah, this is a classic sort of question in mathematics, in philosophy of mathematics. Is mathematics discovered or is it invented? Yeah, I mean, so in some sense, you know, when you're doing mathematical research, you are sort of looking around trying to answer a question. You discover the answer, you can write it down, and then sort of, you know, when you have the proof, it's yeah, philosophically it's quite different to sort of other sciences in that you know, with experimental result, it can also always be falsified by the next experiment. But you know, in mathematics, provided your proof is correct, and it's possible to make mistakes, and people do, but provided the proof is correct, in some sense, like it's then eternally true for all time, and you've made definite progress, and something new has sort of been discovered. Yeah, and it's sort of different to other sciences, at least in some ways. But then, yeah, you can absolutely sort of raise the question, like, well, then wasn't it true all along? And you just you were just discovering that something that was already there. So yeah, there's this sort of on the one view, you invented a new theorem and you proved it. On the other hand, you discovered something that's already there. Yeah, I mean, I guess sort of this is a question which goes back to Plato. It's probably about Platonic. You know, are you discovering a Platonic universe of ideas, or are you just sort of inventing something new? I mean, so I guess my view is like, so Platonism is a pretty unpopular view in sort of philosophy of, there's a question of philosophy of reality, although there are some very prominent mathematicians that hold that view, like Roger Penrose. I mean, from my point of view, like methodologically, like when I'm doing it, I behave as if the world were Platonic, because often what you do find is that there are some really nice results out there. The mathematical universe actually does turn out to be really nice. And what you can often do is, you know, assume the nicest result holds, and then it often does. So I sort of think, from the point of view of actually practically doing mathematics, one may as well treat it as there's a pre-existing universe of ideas that's out there that you're discovering, even if it's not actually there.